Good. So session 6, compasses today. What do we do with compasses? Okay, so we'll go through compass, the application of variation, an awareness of deviation and its causes, use of a hand-bearing compass. So compasses, the basic ideas about compasses. Okay, we use the Earth's magnetic field, also known as the geomagnetic field, and is the field that extends from the Earth's interior outer into space. It's basically the big magnetic field that keeps us protected from the sun and some harmful rays and things like that. But it actually also works as a magnetic compass for us. So as the Earth spins, this magnetic field turns and off it goes. The magnetic field is generated due to the currents and the motions and convections of a mixture of molten iron and nickel in the outer core of the Earth that spins around. So all this melted stuff that's in our core, that spins around our core, is actually what causes it. Okay. While we say north and south magnetic poles are usually located near the geographical partners, they slowly and continuously move over geographical timescales, but sufficiently slowly for ordinary compasses to remain useful for navigation. Okay, so North Pole, the actual true North Pole, and the magnetic North Pole are not the same, and the same in the south. So you can see this line here, true South Pole, magnetic South Pole. Okay, our poles are the axis we spin on. The magnetic north does not have that same axis. And as I said, it is continuously moving, which kind of makes sense because the molten nickel and iron and everything inside the Earth is also moving still. Okay, and they move, definitely move. So our compass points to magnetic north, not true north. Any compass does. Okay, it doesn't know where true north is. It's only looking for that point of literally of this molten nickel core movement of a big fat magnet of the planet. Okay, so therefore we need to make navigational adjustments to achieve true north. Okay, remember we're talking about charts. The top of all our charts are based on true north. So if we want to take something that we've shot with a compass, a bearing we've taken with a compass, have you guys got that window again? That thing that says, please move. You got it. I'll just
stop. We do. Yeah, we do.
Let me just do a stop and a redo there because I don't know why it comes up.
I think it's when people join late.
Oh, okay. Cool. So we'll continue. So where do I get to? So we need to make adjustments, navigation adjustments between where our compass is pointing and where the North Pole is, the true north is on our charts. Okay. So our compasses are also influenced by other magnetic fields. So if you put a magnet next to a compass, it's going to influence it, isn't it? Okay. So onboard magnetic fields, moving magnets, all that sort of thing also influence our compasses. So, variation. Where and what is variation? Okay. You'll notice I put this particular picture up. There's the compass in front of each wheel. Okay. Variation. That's the difference between true and magnetic north. Okay. That's the variation. And in different parts of the world, it's completely different. So variation is the difference between magnetic and true north. It's always north. You don't have a southerly variation. Okay. It varies by location and over time. So depending on where you are in the world and when you are in the world, your variation will change and adjust itself all the time. Okay. In most populated parts of the world, it currently ranges from about 30 degrees west, so where I am at the moment, okay, to 26 to 30 degrees just off New Zealand, off the southern tip of New Zealand. So that goes from one side to the other. So around the world, you've got about a 60-degree difference. Okay, and I'm talking about most populated parts, not talking about standing just right next to it where it's going to be wildly different. Okay, so it could be positive or negative from true north. So in other words, this would be westerly variation. This would be an easterly variation if that's true north. Okay, some parts of the world, it changes. Literally, you can sail off one area and come into another area, but spend a morning in one and an afternoon in the other. Literally, if you sail across it. Okay, so this is a little chart of magnetic variation around the world. The green lines being zero magnetic variation. Okay, the red, west, east. Blue east. Oh, sorry, the blue east, the blue west, the red east. Okay, so you can see as you work further and further and further and further away from the green, your variation increases. So down here where I am, it's around 23 to 25 degrees. In the middle of the Atlantic just here, it's around 30 degrees. As you come down here towards New Zealand, you can see got a much, much bigger variation. Now, this is obviously unpopulated. This is very, very, very far south. But here in New Zealand, it's about 26 degrees. So you can see how it massively changes around the world. You know, up here in England, you're almost on the green. And the same thing with the States. It's not massive changes. You're right down the middle of the States is pretty green. Down here, huge differences. Okay, so where are you in the world makes a big difference to your variation. Where do we find it? Where do we find it so that we know what we are in on our compass rose? There's our true north. It's always on every compass rose. And then quite often, it will have an inner rose for magnetic variation. And that is dated. That is dated to a specific year. Okay, compass rose. So our charts, it forms lines of variation on the bigger ones. Okay, so I don't know if you can actually see it on this size. It may be a little big, but they look like contours. And they contours of variation. So this is North Atlantic. And because it changes so considerably across the North Atlantic, literally we have lines like that look like contours, and that controls your variation across the Atlantic. Okay, and they're usually in purple. Okay, modern GPSs and electronic equipment, they'll have them. So if you've got a fluxgate compass, it'll know what your variation is by knowing where you are and what the time is. Okay. So how do we get this information? Out of a compass rose. So here's our compass rose. There's our true north. Nice little star there. There you can see a nice little arrow coming to one side. That'll be the magnetic variation for where this compass rose is. So it's 4 degrees 15 minutes west, and that was in 2009. And it changes 8 minutes east every year. So that's what that information tells us. Okay, 4 degrees 15 west, that's where that comes from. And the next bit in 2009, and then in brackets, the change. Okay, so these are the magnetic variations at the date shown the compass rose was printed and the annual magnetic change thereafter. So how do we extrapolate that? Okay, we want to basically look at this compass and say, okay, what is today's current magnetic variation? Okay, so what do? Take that same information that we took from there. What is it today? We have an 8 east annual change. tells us that. Okay. So I did this end of last year, so it still haven't changed it. So it's 11 years. Okay. So we've got 11 years by 8 minutes annual change. That means it's 88 minutes of change, doesn't it? That's just a straight maths. 8 years, 11 years by 8 minutes, 88 minutes each change. Okay. So that's 1 degree and 28 minutes each change. Okay. But our base variant, where the base variation was going west, but it's changing back towards north. Okay, so because it's a westerly variant and it's changing to the east, we would subtract the one from the other, and then we would get a variation of 2 degrees and 47 minutes west today, or in 2020. And every single variation on every chart, unless there's almost no change happening, will give you this basic information so that you can correct it for today. Okay, so how do I get there? 4 degrees, 15 minutes west, less 1 degree, 28 minutes east, 2 degrees, 47 west. Remember, there are 60 minutes in a degree. We're not going up to 100, we're only going up to 60. 60 minutes in a degree. Remember that from earlier on? So if we look at that, so we could say that 4 degrees and 15 minutes is 255 minutes in total. 4 times 6 plus 15, 1 degree, 60 plus 28 is equal to 88 minutes. So you could literally then just go 255 less 88, divide by 60. Okay, 167. 167 is 60 plus 60 plus 47, isn't it? 2 degrees, 47 west. So we must always work it back. That's what I'm trying to get across here. Back to 60 minutes making a degree, 60 minutes making a degree, and then whatever is left over. Okay? One thing, when we look at that, we can't split a single degree up here by 47 minutes west. Sorry, 47 minutes. So we would just round that off to the nearest number. So we would say that would be called 3 degrees west. If it was less than 30, we would round it up to 2 degrees west. Remembering that it's half of 60. It's not half of 100. Half of 60, round up one side. If it's past 30, round up the other way. So we would call that 3 degrees west. I mean, we can't even steer a course of a 1 degree change. So if you're trying to steer a 1 degree difference and a half a degree difference, well, you're never going to do that. So we don't worry about it. Okay. So variation, let's give it a go. A little quiz. Cape Town. We're 24 degrees west, 24:38 west, and that was in 2009. And it is a 7 degree west change. So now note that it's going with the change. So it's becoming greater, isn't it? So we'd add the two together. Unlike the previous example, where the one was going east and the one was going west. Give it a go. See if we can work out what variation I'm currently sitting in.
That's 7 minutes, right, Wavy?
Yeah, 7 minutes west. Yeah, no, not 7 degrees. No, that would be a bit extreme. No, 7 minutes west. You'll often find they don't bother putting the minutes in there because it has to be minutes. Any sailor would know that, any person who looks at a chart. Lots of right answers coming. So we've got an 11-year change if you work it to last year again. So that's 1 degree and 17 minutes. Add the two of them, 26. So we would use 26. So we're at 26 degrees. So if our compass points at magnetic north, it is 26 degrees different to where true north is. And that's quite considerable, as you can imagine. 26 degrees difference is a lot. So if we have a look a few back, that's the variation there. And it's only 2 degrees. What do we work it out as? 3. So that's 1, 2, 3. Cape Town is 26. So you could be 26 degrees out just steering a course, which, as you can imagine, could get you in all sorts of trouble if you don't do it carefully. Okay, so then what is deviation? Deviation. That's the magnetic deviation is an error incurred in a compass by a local magnetic field, which must be allowed for. So along with magnetic variation, you've of course that's still there. If accurate, bearings are to be calculated. So if you want to accurately calculate or steer a boat on a compass, you need to work both variation and deviation. Deviation is what's on your boat. The engine, the electrics, all those things that can actually build up a magnetic field. And then we actually take the boat out and we swing the compass. And we say, when the boat's pointing that way, that's where the deviation is. And when the boat's pointing this way, that's where the deviation is. And we make up a deviation card, knowing at what point of the compass and how much it is. Okay? But that's for the nice fixed items on board. Not such fixed items, like somebody putting a speaker by a compass because they want to listen to music in the middle of the night, and that speaker has got a whopping great magnet in it. That will throw your compass out. It is still deviation, but it'll throw the compass out enormously. Engines, whether they're running or not, create a magnetic field. Electricity has a magnetic field to it. Okay? Anything in the proximity of that will swing that compass around. Okay? That is magnetic. So the stainless steel frame behind and the plastic frame underneath does not affect it. It must be a ferrous metal. It can't be a non-ferrous metal. Okay. So some of these installations are fixed, some are not. There we go. So we would take the boat, we would point it one way or the other, and we would start it at 0, and we would slowly but surely, knowing fixed points on land, we would point the boat right round all the way down to 360 degrees, and we would record the deviation on board. So as the boat changes course, the deviation changes, and we would record it as we go. This is a deviation card, okay? Also known as swinging a compass. If you swing a compass, you're finding out what the ship's magnetic field is. You'll notice it makes a very neat curve, okay? They pretty much always do, because the engine's stable. But because of the variation in the magnetic field of the Earth, it pulls the compass one way, then it pulls it the other way, okay, as the boat spins. Okay, so if we combine them both, we want to work things out. We combine both variation and deviation, okay? So we look at it. Take variation and deviation together, and we get our compass, okay? So true north. That's on our charts. Okay. Then magnetic north, compass north, and so on and so forth round. Okay. So there's our heading. Okay, compass, okay, deviation, magnetic, true. So deviation, variation. So you will notice that we've split it. Your compass heading includes both. Your magnetic heading only includes variation, and your true is obviously true. So we've got actually 3 different headings. Okay? Compass, magnetic, and actually true. Okay? True is the one on the chart. Oops, sorry, jump to there. Magnetic, the magnetic north, is not taking into account any deviation, and the compass is deviation plus variation. It's the 2 together. The reason we get the 2 together when we look at a compass on a boat, and we call it compass heading, is because it is a fixed unit and you can swing it and you can make one of those. You can make a deviation card for it. It's fixed, the engine's fixed, the electrics and everything else is fixed on board. Okay? So, whereas a magnetic compass, just a handheld compass, you can't make a deviation card for, because you're going to move around the boat with it. And then you move it to another boat, and then it'll be different deviation. So you don't make deviations for magnetic compasses, handheld compasses, only for fixed compasses. So if you want to remember a nice acronym, true virgins make dull company at weddings. So we've got true, our table, our chart, true. Variation, then we get magnetic. Deviation, then we get compass. And then we would add west. So if you reading it like that, you would add west if you're going from true to magnetic or magnetic to compass. What do I mean by add west? Okay. You have a westerly and an easterly variation and deviation. You remember that? I'm going to go back a little bit. There's my deviation card. That's nothing, no deviation. That's a westerly deviation. That's an easterly deviation. So we need to know which way we go with west or east, whether we add or subtract it. So if you're going down from true, variation, magnetic, deviation, compass, you'd add west, which means you would therefore subtract east. If you're going the other way, you'd subtract west and add east. So you can look here, we've got true 120 degrees, we would add the west, so 26 degrees west, the one we just worked out, so 146 degrees magnetic. But if you had a deviation card that said 26 degrees east, you would then subtract it this way around. Okay. Same here, 120 degrees. Because it's easterly, we would subtract. Because it's westerly, we would add. Okay. And as soon as we go up the other way, as soon as we go from compass to true, okay, compass to true, we would subtract west, add east. A Portland plotter makes it easy for you. It actually puts it there for you. So you can just put your variation there and it'll add and subtract it. Don't need mathematics to do it with a Portland plotter. So your compass reads 120 degrees. Your variation is 26 degrees west. Your deviation is 6 degrees west. What is your true course? So what would you put on your chart? So true, oops, sorry, true, we've got our variation, we've got our deviation. If we're adding west that way, we're subtracting west that way. We're subtracting it if you're going from compass to true. So 114 less 26, 88. So that goes back right back to our, if you remember the acronym, and the reason we use it is so that little bit at the end, add west at wedding. So if you read it that way, you'll always remember to add west if you're going that way, which means you subtract it if you're going the other way. Okay, so let's do another one. Got a split here. Your compass course, sorry, your chart course is 120, your variation is 19, and your deviation is 3 degrees. What course are you going to give your helmsman to steer? So he's standing behind the wheel in front of the compass, and you've got to give him a course. So now you're going from true to compass. Now they're coming out thick and fast correct. So now we're going the other way around, starting in true. So you've decided, you put your Thornton plotter on your chart and you decided that's where I want to go. You have a look at your variation, you calculated for it for the year. You know it's 19 west. Okay, and you add the 2 because we're going down, aren't we? Add 2, but there's an easterly, so take those 3 east off, and that's the compass course you'd give your helmsman to steer, 136. Handheld compasses. Handheld compasses, these sort of looking things. Okay. What is a marine handheld compass? Okay. It's a waterproof compass which gives you a bearing to a specific object. Okay. Note that this one has a little line there. That is what you shoot your bearing on. Okay. Must have accurate capabilities. So you can line that up with a lighthouse, with a buoy, with the top of a mountain. You need to be able to line up a specific point. Okay. Land-based compasses, this one you can use because you see it's got an accurate line here. I can tell you from experience, they rust and fall to pieces in about half an hour. They're fairly useless. They don't work terribly well. Okay. This sort of thing you can't use because you can't get an accurate bearing on it. It doesn't have that nice line. Okay. Your phone may have a compass on it, but you can't line it up accurately. You need to be able to get that accurate reading. So you need something like this. Okay. This marine-based compass. You'll notice this sort of phosphorescent stuff around it. You put a torch on that, you can use it at night. It glows like a watch. In fact, they glow bright. You can read them easily. They really are good. Okay. Remember, handheld compasses don't have deviation. So there you can see, it's got a line there, and he's got an accurate sight to be able to take a bearing on something. So a couple of things to note in this pick. Take careful note of the magnetic field around you. Remember, you don't have a deviation card. Stand well clear of anything that you think could cause any magnetic interference. So don't sit on top of the electrics box or the switchboard or the engine. Get yourself nice and clear and away of everything so you don't have any deviation. Okay? Make sure you're steady. Trying to get a decent reading using a handheld compass if you're bouncing around is next to impossible. Take multiple readings. So if you're shooting a reading at a lighthouse, shoot it 3 times. So I'm shooting this lighthouse. I've got 138. Now I've got 137. Now I've got 139. Okay, I'm going to call it 138. Get someone else to write your readings down. Because if you're doing something like a 3-point fix, the more, or the quicker you can, it's a terrible word, the quicker you can do a 3-point fix, the more accurate it's going to be, remembering that the boat is still moving while you're doing it. Okay? So having somebody else write them down, rather than shooting one, putting it down, writing notes, picking it up, shooting the next, you can go from site to site to site very quickly. Always have the compass attached to you. You see this wrap around his wrist? You want to have the ability just to drop it and grab hold of that guardrail. So you can go for that, one hand for yourself, one hand for the boat, immediately. 90% of these things, and I go back a few, are very rubberized and can be dropped. See, he's got that big rubber frame around him. It's designed so you can just drop it and grab something. The lanyard around your neck, it's not going to get damaged, but you can grab. Okay? So always have it attached to you. They're not cheap. You don't want to throw them over the side particularly. Okay? So, compasses. Quite simple things. Not terribly complicated. It's just getting over that initial hurdle of understanding variation and its relation from the planet Earth to us on the boat. And then adding that deviation. What is all this electrics that's on the screen now? It's directly almost below the compasses, isn't it? For those who've been on board. The wheels are almost directly above this, aren't they? Either side. How much does all those electrics influence those wheels? Those compasses, you know? So that's that deviation side. So now we've understood the variation. That's going to change. As we go around across the world, it's going to change one way, then back again the other way. But this lot, this is going to be the same on board the whole way. So when we're working out our compass courses for our next leg, we go, okay, what part of the world we're in, there's your deviation. That's fine. Okay, now what are we going to do with our what part of the world we're in, that's our variation. Now we pull out our deviation card and say, okay, we are steering a course, magnetic course of 200. How does that fit on the deviation card? Do I add or subtract west or east? Inversely, you know, you say to somebody, what course you've been steering? And they'll tell you 200. And then you can go down and take that compass course, remove the deviation or add the deviation. Then we get a magnetic course. Then you'd work out your variation, west or east, add or subtract, and then you get your true, and you can put that onto a chart. So it still works absolutely brilliantly, and it's a nice, easy way to give somebody an easy course to steer. Trouble with these electronic instruments, you put a waypoint there and a waypoint there, and it works it out, and it tells you, no, you want to steer a course of 119.3. You get a helmsman to steer 120 degrees in a straight line, you're winning. You give him 119.3, the poor guy's going to have a flat spin. He's never going to even attempt it. So a nice piece of paper, a nice round number makes a big difference sometimes. Okay, so again, that's just kind of scratching the surface of the compass. We do go into a bit more depth, and we do a lot of exercises with it, both in the classroom and at sea. We do loads and loads of examples when we're sailing. 3-point fixes and a hand-bearing compass is part of any exam. Any sailing exam, it's always going to be there. Funnily enough, I don't know if I've mentioned it before, commercial vessels, if they have the ability to do a 3-point fix with a hand-bearing compass like that, they have to, because of the errors with our GPS fixing and human reading and things incorrectly. Paper chart, visual navigation, passage making is definitely part of your exam. So being able to fix your position and then plot your position and a course from true on the chart up to compass, and inversely from compass to true on your chart. So I think both of those is definitely part of all the exams. And this could be an exam in the States, it could be an exam in England, South Africa, Australia, it doesn't make any difference. They all have these things in every exam. Using them. You look well cool if you do a very quick and a good 3-point fix. You come up with a compass, you write 3 numbers down, you go down, you go plot, plot, plot on a chart, and you go, we are there. It looks very impressive. Practice it. It's great fun. Cool. Next week's session, we'll talk about some tides and tidal streams. Okay, so we'll do some tidal definitions, levels, datums, things like that. We'll talk about tide tables. We'll talk about the use of the Admiralty, the method of determining the tidal height for a standard port, and we'll talk about the awareness of secondary ports. Okay, so what we want to do, Andrew, we've got that Portsmouth tidal curve. I wonder if we can put that on the group.
Yep, I'll put it on the group, Facebook group, and I'll send it as well for pre-reading
next week, because we actually want to use it and do a bit of work ourselves. So we'll actually do some tidal calculations ourselves next week. And then a bit of tidal diamonds and stream atlases. So again, next week, pen and paper, and we'll actually do some tidal height calculations and a little bit of calculations with a tidal diamond. Cool. Guys, any questions? Anything going on, guys? How was that?
Fantastic. Thank you.
We know what a difference between true, magnetic, and compass.
Yeah, that was brilliant, Wavy. Thank you.
Yeah, it's a pleasure.
Very good.
Wavy?
Yeah, good to put it into practice, and then obviously as you're doing practice, you're obviously going to get better at it.
Yeah, well, I mean, when you first pick up a hand-bearing compass and you do your first 3-point fix, your triangle tends to be quite big. And then as you get used to the compass, you get used to using it, you start shooting more and more accurately, and that little triangle gets smaller and smaller and smaller with time. And it's just, it's practice. Practice makes perfect. And you just get used to shooting with a compass. I mean, if you think of the common uses of using a hand-bearing compass on board, the most common is seeing if you're going to have a collision. You pick it up and you point it at a ship and you go, okay, he's at the bearing at. 10 minutes later, you point it at the same ship. If his bearing's the same, you know you're on a constant bearing closing range, which is then collision course, isn't it? And we spoke about that right in the beginning, didn't we? So that's just a hand-bearing compass being used to prevent collision, not even navigation, you know.
Wavy, Tracy asked a really good question in the chat, which was how often is the compass swung to create the deviation card?
Whenever there's any, good question, very good question, but whenever there is any major change to the electronics of the boat or the engine, gearbox, or you know, something big like that, you know, if we added a small pump, that really wouldn't affect the boat. But the fact that, okay, for instance, I can use Bermuda as a perfect example. I had to go out and swing the compass again because we got a brand new generator. We had the old generator on board, it died. We got a brand new generator and it threw the deviation card completely. So we had to go and then put a new deviation card in by swinging the compass. So if something big like that changes, you need to do it. It's, for small changes, you know, you change the pots on board, things like that, it's not a problem. Realistically, you can do adjustments to compasses, but that'll get it down maybe a few degrees, but you can't, I've never ever had a compass on a boat which is actually, they've managed to zero all the deviation with little magnets. There's always some deviation, you know. So I just find it easier to have a deviation card rather than trying to swing it and then magnet and then swing it and then magnet it. Because as you put a magnet in one side, it affects the other side, doesn't it? So you can go backwards and forwards, desperately trying to do it, and it never comes right. That answer your question, Trace? Yeah, good.
Ivy, on older boats, you'd have a big balls either side of the compass. big metal balls either side of the compass on older boats.
Yeah.
Yeah. So with that how's that been replaced now?
Well, there's just more design and build of compasses. Okay. Jim, the world supplies compasses basically in 4 areas. Northern Hemisphere, you just buy a Northern Hemisphere compass. Southern Hemisphere is broken up a little bit more into 3 areas. So if you're buying a compass to use in Cape Town, you'd need to buy it from Cape Town. Just because of, if you remember that the chart I put up of the world, and at the Northern Hemisphere is pretty even, whereas the Southern Hemisphere had these huge chunks of wildly different stuff. Okay. Originally, you used to drop magnets in horns and things like that to hold the compasses, Northern or Southern Hemisphere. You still get that, but it's just easier now to buy a Southern Hemisphere and Northern Hemisphere compass. Does that answer your question there, Jim? Or you happy? It doesn't mean to say the compasses on our boats we've changed because they're in the wrong part of the world. We've just added magnets as we change, as we go around the world.
Another question in the chat from Colin is, in the pre-reading, there was about dip error being different in different hemispheres. So how do you...
That's exactly what I'm talking about.
Yeah.
That's exactly, that is to do with where in different hemispheres, your dip error of your compass is slightly different. So
the question was, though, for a boat like Bermuda, where we sail from Northern Hemisphere to Southern Hemisphere, how does that...
That's what I'm saying. With the dip error, when you buy a modern compass, it's got a little sort of plastic thing about this big that it's got slots. So you just lift the compass up and drop them in, and then adjusts for your dip error. And on the, when you buy it, it actually has, okay, but this magnet and this magnet for Northern Hemisphere, this magnet for Southern Hemisphere, and then there's 3 different brakes for the Southern Hemisphere. Okay, and they have various magnets for it. Okay, so when you're buying around the world, it literally is one that you can use everywhere. Otherwise, you just buy a Northern Hemisphere one, you don't have to pay the extra money for all that lot. They do work, but the dip area is slightly bigger, you know. So they'll pretty much point north to, but it's just a slower, it's not a really great way of doing it. And you can correct them. Really, the biggest errors with compasses is not dip errors and things like that. It's adding west or subtracting east or something like that. That's on variation. That's where I see the biggest errors being made. And the most common thing these days is either cell phones or speakers throwing out your course. I mean, literally, I went to bed the one evening, woke up, and I'm like, why is the boat beating? And the guys were, are you on course? Yes, we're spot on course. And they put this whopping great speaker next to the compass. They were almost 100 degrees out because they put a speaker there, and it had swung the compass round. They were holding the correct course, but the speaker had swung the compass 100 degrees in the wrong way. I'm like, we shouldn't be going upwind, we should be going downwind. I wasn't well pleased.
Wow.
Yeah, who's that? Mark, great sounds, wrong direction. You spot on. No, not one direction. Any other questions, guys?
Nope.
Nope. Well, thanks for joining us again. A couple of weeks left, and then yeah. I hope it's been useful. I hope you guys are learning something, and it's not just, oh, let's just do something just because it gives us something to do on a Friday night in Longdown.
No, it's brilliant. Really great. Really enjoying it.
Thank you.
Definitely worthwhile.